that are formed through diazonium chemistry. So what does that actually mean? Well, it turns out that one of the reactions you can do with amines, and it has to be a primary aromatic amine. It cannot be anything other than primary aromatic amines. Okay? But we can treat them with an acidic solution of nitrite salts. So typically people will use sodium nitrite in HCl. And don't worry about the mechanism just yet. We'll get into all of those details on Wednesday in lecture. But what this ultimately does is the primary aromatic amine under these conditions will end up getting converted to an aromatic diazonium. And this is in very, very useful chemistry. It turns out once you make this aromatic diazonium, there's a whole bunch of different things you can do with this. And we'll get into all of that on Wednesday in lecture. But one of the things that you can do, which you're going to be doing today, is you can take the aromatic diazonium and add to it an electron-rich benzene ring. And what that's going to do, you know, if you think about resonance forms, that negative charge here kind of localizes at the para position, ortho and para, but usually more often para. And so what's going to end up happening is, let's go ahead and draw that resonance form out. So what's going to end up happening is this electron-rich benzene ring is going to go and attack the diazonium species. And so what you end up getting is something like this. And then upon deprotonation, you end up restoring the aromaticity of the system. And this is an Azo dye. So, by saying it's a dye molecule, what that sort of implies is that it would be a colored molecule. Which means if it's colored, it means it's absorbing in the visible region. So does that make sense? You know, think about the reactants, phenol, aniline. I mean, these are small, simple aromatics. We've been characterizing aromatic compounds and talking about aromatic compounds for quite a while now. And in their UV spectrum, as with all simple aromatic compounds, you would see two major absorption bands. You'd see a K band somewhere in the 220, 230 range, and you would see a benzenoid band or a B band somewhere in that 260, 280 range. All right. Both of which well into the ultraviolet. So how is it through the combination of these two reactants that absorb well into the UV that you're getting a molecule that's absorbing way out into the visible? How is that? What is it about the product that's so different than the reactant? Yeah, it's the length of conjugation. I mean, you compare this and this to something like that, there's a whole lot more conjugation here. And as we've talked about since the first lab of the semester, the longer the conjugated system, the longer the wavelength of absorption. And so through the combination of those benzene rings through that azo linkage, we've more than doubled the conjugation of the system and caused a dramatic bathochromic shift as a result. Okay. Any questions about that so far? Okay, so that is what you're doing today. You're going to synthesize your dye molecule. When we go to characterize these, you're going to be characterizing them under three conditions. You're going to be analyzing your dye under neutral, so pH 7 buffer conditions. You're going to be analyzing under strongly acidic and under strongly basic conditions. So what that suggests then is that if we're looking at these different these dye molecules under differing sets of pH conditions, what that suggests is that pH is going to cause a shift in the absorption. So how is that? Why is it just changing the pH? Why would that have an effect on the absorption of these molecules? It has to do, and it's going to depend on your specific dye molecule, because the different dye molecules have different ionizable groups. But imagine for a minute, if the phenol is an ionizable group, okay? The phenol has a pKa of 10. Now I'm going to take you back to Gen Chem here, just to refresh your memory, because it's a really important relationship to remember. Because this has an ionizable group with a pKa of 10, I can, under the right conditions, deprotonate it. Now, theoretically, that should have an impact on the absorption of this dye molecule, right? Because this thing in its deprotonated form has a whole lot more electron density on the oxygen than it does here. Meaning there's a whole lot more electron density being pushed into this system. So in a sense, by deprotonating, dramatically increasing the electron density being pushed into the ring system, we are kind of lengthening the conjugated system through resonance, right? There's a lot more contribution of that when you have no proton there. Okay? So what we tend to see is with these ionizable groups, deprotonating tends to cause a lengthening of the conjugated system via resonance. And if that's true, we should see that reflected in the UV spectrum, the visible spectrum for this. Now the question is, under what pH conditions is that going to occur? Okay. So remember, when we're talking about these kind of ionizable groups, we oftentimes will represent them kind of in a shorthand way. So if everything's protonated, I can think about this as HA. So normally how we represent these. In the deprotonated form, I'm going to think about it as A minus. Now, there's only one condition where the protonated and the deprotonated are going to be present in equal amounts. This has to do with the relationship between pH and pKa. Now, before I get too far into this, I just want you to remember a very, very important thing. pH is variable. I can adjust the pH of a solution to anything I want. I want it more acidic, add some HCl. If I want it more basic, add some hydroxide. You can adjust the pH to be whatever you want it to be. The pKa is a constant. You cannot change the pKa. The pKa for a functional group is always the same. If I'm talking about a phenol, the pKa of phenol is 10. It can never be anything other than 10. But I can change my pH. So under what conditions of pH am I going to have equal amounts of these two things in solution?
7.
It's the most common answer I get all the time, and it's not. It depends on the acidity of the ionizable group. The only time you're going to have equal amounts of these in solution is when the pH is equal to pKa. That is where HA concentration equals A minus concentration. So if I were to take this phenolic dye that we've been dealing with, and I were to put it in a solution of pH 10, then you would have equal amounts of protonated and deprotonated present. At any other pH condition, one of them is going to predominate. So let's say, for instance, the pH is lower than pKa. So this causes people a lot of stress sometimes, trying to remember the pH-pKa relationship and relating that to protonated versus deprotonated. It's kind of a lot of mental gymnastics sometimes for people, but what I hope to show you is that it's not difficult. The way I always remember this is I think, okay, if pH is lower than pKa, what that's really saying is that the pH of the solution is more acidic than the pKa. Well, if it's more acidic, that means there's lots of protons around. And if there's lots of protons around, the protonated form predominates. So where the pH is lower than pKa, the protonated form wins. Okay? The other choice would be where the pH is greater than pKa. So this is just kind of the opposite scenario. Here we're looking at a case where the pH is more basic than the pKa. Well, if it's more basic, there aren't protons. And so the deprotonated form will predominate. All right. Any questions on those relationships? So this is not only something that's useful to know for this lab specifically, but this is just really good kind of foundational chemical knowledge to just file in the back of the head. Okay, so the phenol is not the only ionizable group in these dye molecules, okay, because what can happen under the right conditions, you can actually protonate the azo linkage. So you could, I'm just going to abbreviate this as pH for the time being. This thing has a pKa around 6-ish. So imagine for a minute, what form would predominate if we took an azo dye and we put this in a pH solution of 2? What form would predominate? Between these two, the deprotonated azo linkage or the protonated azo linkage?
The protonated.
Yeah, in this case, the protonated would. right? I know that because, well, I can just read it off the board, but we could rationalize it by saying, in this case, the pH is lower than the pKa. And again, if the pH is lower, that means it's more acidic than the pKa. If it's more acidic, lots of protons and the protonated form wins. Okay? So that's why I would say that we would expect the pH solution 2, this form is going to predominate in solution. Now, how does that affect the absorption? Why would protonating this have any effect whatsoever? When in doubt, draw a resonance structure. So the resonance form of this, I could break the pi bond and give the lone pair to that nitrogen. You see what's happening to the conjugation there? So, let me just draw in that benzene ring so I make it a little easier to see. You see how by protonating the azo linkage, we have, I don't want to say eliminated the conjugation between the rings, right? Because this is a resonance hybrid, but through protonating, we've certainly weakened the conjugation between the rings.
Wait, isn't that the deprotonated?
No, this is the protonated form.
Okay.
This is the deprotonated. Right, there's no protons on the azo linkage.
Okay.
Here we have the proton on the azo linkage.
Got it.
So through protonation of the azo linkage, we've certainly weakened it as a result of this resonance form. So by decreasing the conjugation through the system, we might expect to see a hypsochromic shift in the UV spectrum. Okay. So that's how these different ionizations can affect the azo linkages, the azo dyes, and their absorptions. And that's why we're going to be looking at the dye molecules that you make today under a variety of pH conditions. Okay. Any questions on that? Okay, so that is pretty much it for our azo dye discussion. I don't want to go into too much detail on procedure because you each have your own procedure depending on the dye that you were assigned. So the only thing that I will mention is some of these dyes, you know, they're all different molecules, so they have different solubilities. Some of these dyes are very, very water soluble, and you'll end up with a nice uniform solution of your dye solution. Others are not as water soluble. And if you get one of those not so water soluble dyes at the end, you know, the way you'll recognize it is it'll be rather opaque. So it'll look like there's a bunch of solid in it. If you get one of those kind of more insoluble dyes, you'll probably need to do a filtration step. So just a simple vacuum filtration, because you don't want a bunch of solid in your dye. If you have a really heterogeneous precipitate kind of dye solution, when you go to measure the visible spectroscopy, all of those solids are going to affect your spectrum. So you don't want a bunch of solid as you go and take your spectra on Wednesday. Okay? So if you do the synthesis today and you notice that you've got a bunch of kind of a chunky solid stuff, go ahead and do a vacuum filtration. And that way, whenever you come in on Wednesday to do the spectroscopy, you'll just have a clear dye solution to work with and you'll be ready to go. Okay?
I just wanted to clarify what you were saying before. So when you're protonating and deprotonating, you're talking about the hydrogens on the nitrogen, not like the OH, right?
Yeah, well, I mean, either one can go. I mean, depending on what the pH of the solution is. So if this is under strongly acidic conditions, well, then you can get it, much below a pH of 6, and you're going to end up protonating the azo linkage. But then on the other end of the pH scale, you start getting into a very basic solution beyond 10, then you're going to start to deprotonate the phenol.
Okay.
So it just kind of depends on where the pH is as to what specific ionization state predominates.
Okay, thank you.
Any other questions on this?
So you also said that the form where the OH is protonated, right? It's more conjugated. So
No, the form when it's deprotonated.
I mean deprotonated, it's
Mhm.
more conjugated, right? So that pushes it more to the visible spectrum.
Yeah, it should push it out to longer wavelengths.
So if I don't know if this is true, but like if our dye is like there's more color to it, right? Can we assume that it has more protonated?
Well, not necessarily more color. It depends on what wavelength of color. Because if you were to look at this and we were to think about putting it in a strong base solution, theoretically we would predict that you should see, as you deprotonate the phenol, a shift to a longer wavelength of absorption. So, and it's not going to be dramatic for most of them, but it might be like, say, 575 for this, maybe 600 for the deprotonated form. So a subtle shift in the bathochromic direction as you deprotonate the phenol.
That makes sense.
Now, when you're talking about longer wavelengths being absorbed, what we see is going to be opposite of that, right?
Yeah, that one always confuses me. I have to think about that.
Because if it's absorbing, we're not seeing it, it's taking it.
Yeah, so if it's absorbing longer
So
wave
it's like absorbing red. We don't see red, we see green.
green, yeah. And if you were absorbing purple, for instance, then it would appear
Like
yellow.
orangey yellow.